Hello and welcome to another video for Calculus 1. So starting this video, we are formally going to start the integral part of the calculus. So in this video, we are going to discuss about approximating areas under the curves. So the method that we use to approximate the area under the curve is the Riemann sums, which basically the idea behind the Riemann sum is, so for example, I have a curve here, let's say this is the curve of f of x. And then I want to approximate the area from, let's say, point A to B. Okay, so I want to approximate this area right here. So this is the area that I'm going to approximate. I want to find the area of this region here. So the idea behind this Riemann sum is we will divide this region into small rectangles. So I'll divide this into smaller rectangles. Okay, so I'm going to construct rectangles here like this, and then we'll find the area of these rectangles and then we'll add them up, and that gives the approximation to the area. Because see, if you look over here, I'm losing areas right here. So when I construct this, how many did I construct here? So 1 2 3 4 5 6 7 8. When I construct 8 rectangles, see, I'm losing this area. So obviously this is not going to give me the exact area. But the idea here is we will keep increasing these rectangles. So more the number of rectangles, better the area we are going to get. So eventually our goal is to, so if I say n is the number of rectangles, okay, that I'm making here. So if I take n to infinity, or if I construct infinitely many rectangles, then the area that we are losing here approaches to 0, which means we are going to get exact area. So we are going to make infinitely many rectangles, and we are going to add up those area of those rectangles, and we are going to find the exact area under the curve. So that's the whole point of doing all of this. Okay, that's the whole point of integration. So we'll see that gradually we'll increase the number of rectangles, and we'll see, and then we'll take it to infinity, and then we'll see what the area is going to be. So let's start with this definition here. So again, for any continuous function defined on a closed interval AB to approximate the area of the region under the curve from point A to B, what we do is we will divide the region into subintervals. Okay, so we'll divide that into subintervals um, like this. Okay, so x0, x1, x2 are the points that's dividing that region into intervals. So for example, if I have that curve, then I want to find the area from A to B. So what I'm going to say is this A is x sub 0, and I'm going to take points here like this. So x sub 1, x sub 2, x sub 3, all the way to x sub n. That means I'm going to make n rectangles here. Okay, so the width of the, so we are going to construct rectangles such that the width of the rectangle is uniform. So width of the rectangle is given by b minus a over n. So how many rectangles we are going to make? Okay, so these sub-intervals that we constructed are called the regular partition. They are called regular partition because we have the uniform width, equal width of those sub-intervals. Okay, and then these points x sub 0, x sub 1, all the way to x sub n, those n points are called the grid points. So we are just creating a grid over there. Okay, then the kth grid point x sub k is given by a plus k times delta x. So which means the position the x1 is given by x0 plus 1 times delta x. So that means when we add delta x to x0, we get x1. Now to get x2, we have to add 2 delta x to x0 so that we get x sub 2 and so on. Okay. Now the area under the region is approximated by a sum which is called Riemann sum, which is given by, so delta x is the width of the rectangle, and f of x sub k star, these is any point on that interval. What happens, so let's draw that. Okay, so for example, I have that curve. So let's say this is x sub 0, this is x sub 1. So I pick any point on this interval. So let's say if I pick here x sub k star, okay, then this is the height of my rectangle. That means I'm going to construct the rectangle like this. And so this height of the rectangle is given by the value of the function, or the y value of the function at that chosen point, which is x sub k star. Okay. And then when I multiply the width, which is delta x, by this height, f of x sub k star, then that gives me the area of this rectangle. That's what this means. Okay, then we do that for each of those rectangles, or to those n rectangles, and we add them, and that gives us the approximation of the area. Now, how do we choose that x sub k star to determine the height of the rectangle? So we could do that in, usually this is what we do, and is we can pick any point, but usually this is what we are going to see with the examples. We can do this in 3 different ways. We can choose this left end point of the subinterval as the height, so that gives us the left Riemann sum. If we choose the right end point as the point to determine the height of the rectangle, then that sum is called the right Riemann sum. And then we can also choose a midpoint between those two, and that gives us the midpoint Riemann sum. Let's see this in a graph in the next slide. Okay, what does that exactly mean? Okay, so I have 3 different graphs. So I'm going to show you left Riemann sum, right Riemann sum, and the midpoint Riemann sum. Okay, so for example, I have this curve. I want to determine the area from 0 to 1. Okay, and I'm going to divide this into, let's say, 5 subintervals. So this is x sub 0. So let's say this is x sub 1. This is x sub 2. This is x sub 3. This is x sub 4. And this is x sub 5. Okay. Now, when I say left Riemann sum, the height of the rectangle is going to determine by the left endpoint of the subinterval. So our subintervals here are x sub 0, comma x sub 1. That's the first subinterval. And then x sub 1, comma x sub 2 is the second one, and so on. So now, the first rectangle that we have here will have the height determined by f of x sub 0, or the height right here in the left endpoint of this interval. So the height here is 0. So this is the rectangle. I mean, the area of the first rectangle is just going to be 0. Now for the second rectangle, the height is determined by x sub 1, or this height. It's the height of the second rectangle. This is how I'm going to construct the second rectangle. Now the height of the third rectangle is determined by x sub 2, or the left. So this is the first one, first subinterval, second. So for the third one, it's determined by x sub 2. So we draw the height up here, and then that's the rectangle. Now for the fourth one, this is the height. For the fifth one, this is the height. Okay. And for the, yeah, that's what we have. So we are going to add this area. So for the first area, first area is right here. The area of this the area of this rectangle right here. Sorry, this is not working. Okay, so this area plus this area plus this area plus this area. When you add this, that gives us the left Riemann sum. Now, how does the right Riemann sum looks like? So now if we take the same graph here, and then we divide. So this is x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. Now I'm going to take the right endpoint. So from the first subinterval, x1 is the point that I'm going to take to determine the height of the first rectangle. So from here, I'm going to construct the height of the first rectangle. So this is going to be my first. See, the first rectangle here was this rectangle with zero area. Now I have a taller rectangle. The first rectangle is taller. Now the second rectangle, I'm going to determine by the height of the second rectangle is going to be determined by x sub 2. And this is how I'm going to construct that. So third rectangle, now the fourth rectangle, and the fifth rectangle. Now this area I'm going to add this area, and then this area, then we have this one, and that area. That's going to give us the approximation of the area under the curve. So if you look over here in the first one, we are losing this area here. Here we are gaining this extra area. So both of these are not accurate, but that's just the approximation. And again, the idea that I talked in the previous slide is as we increase the number of rectangle, either the area that we are losing or the area that we are gaining is going to decrease. And when we take n to infinity, that's going to give us the exact area. Now let's see what does the midpoint would look like. So again, x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. I still have the same point. Now the height of the rectangle, when we do the midpoint Riemann sum, we are going to take the middle point in that interval. So when we do x sub 0, x sub 1, we are going to take a point that is the midpoint of these two. So somewhere here, the midpoint here. So in each interval, we are going to take the midpoint, and that point is going to determine the height of the rectangle. So here, I'll draw that height. So that's the height of the first rectangle. See here, it is shorter than this right when we take the right endpoint as the height, and it is taller than when we take the left, so it's the middle one. And then here, this midpoint is going to determine the height of the rectangle. Here, this midpoint is going to determine the height of the rectangle. This midpoint is going to determine the height of the rectangle. And this midpoint is going to determine the height of the rectangle. Now, if we notice here, we are gaining some area, we are losing some area, kind of like there's a little bit of balance here. Again, this is also not going to give us exact area, but we do consider that this midpoint is a little bit better than either of these. So here we are losing a lot of areas. Here we are getting a lot of areas. Here, if you look over here, we are both losing and gaining. So here we gain this area, and then we lost this one. We gain this one. We lost this. We gain a little bit here. We lost this one. So kind of like there's some kind of balance here, but again, it's not exact. That's going that we'll have some errors here, but that looks a little bit better than these two. Okay, so that is the whole idea of Riemann sum. So we have three different types of Riemann sum: left, right, and midpoint. So we are going to see examples, and then we'll evaluate the area. Okay, now let's look at the first example. So our function is f of x equals x squared, and I already drew the graph here just to make it easy. I'm not good at drawing graph by hand, so I already have that. Now we are going to find the area under this curve and above the x-axis from x equals 0 to x equals 2, and we are going to take n equals 4. That means we are going to take 4 subdivisions, and then we are going to evaluate a left Riemann sum first, and then we'll do right, we'll do midpoint, and we are going to compare the area. Okay, so let's start with the first one. So always the first thing that you are going to do is to determine the width of the rectangle, which is given by delta x equals b minus a, or the right endpoint minus left endpoint, divided by how many rectangles you want to make, and it is n equals 4. So this gives us 1/2, or we can also say 0.5. So that's the width of the rectangle. Now either we can start by writing the subintervals, or we can go to the graph. So we are going to go from 0 to 2, and we are going to divide that into 4 rectangles. So 1, 2, 3, and 4. So first one is 0. So x sub 0 is just 0. X sub 1 is, so we go, the width is 0.5. So this is 0.5. Plus 0.5 is 1. Plus 0.5 is 1.5. Plus 0.5 is 2, which is right here. So our sub-intervals here are, so sub-intervals are 0 to 0.5. Then 0.5, when we add 0.5 to 0.5 is 1. And the next one is 1 to 1.5. And then 1.5 to 2. So those are the sub-intervals. So those are the endpoints for the rectangle. So for the first rectangle, we are going to take left endpoint as the height. So we are going to find the height. So we are going to find the height at this one, this one, and this one. So those 4 points are going to determine the height of the rectangle. So the heights are f of 0. So we put it here. So f of 0, which is 0. Then the second one is f of 0.5. So we'll put 0.5 here, and that gives us 0.25. Then f of 1, which gives us 1 squared is 1. The next one is f of 1.5. So 1.5 squared is 2.25. So these are the height of the rectangles. Okay, so this 4. So that means the height is determined. So let's go ahead and draw the rectangle. So the first rectangle has a height of 0. That means it's just a rectangle here, this rectangle right here. Second rectangle, the height is drawn at 0.5 and it is 2.5. So this is the height of the rectangle, or this is the rectangle. And the third rectangle at 1 goes to 1, and this is the rectangle. Fourth rectangle right here. So this is the area that we are looking at. So this one, the first one is a 0. This is the second one, the third one, and this is the fourth one. So that is the area that we are going to find. So the left Riemann sum with 4 rectangles, so usually we write L sub 4, is given by delta x times, if you go back to the definition here, so it is given by delta x times the height. Okay, so delta x is 0.5. So let's write the formula. So f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus f of x3 times, so we don't go to x4 because we are taking the left endpoint. So this one, this one, this one, this one. So those are the one that determines the height, okay, because we are taking the left Riemann sum. So this is 0 times 0.5. F of x1 is 0.25 times 0.5. F of x2 is this is 1 times 0.5 plus 2.25 times 0.5. And when we put this into the calculator, we'll get 1.75. Now the next question, we are going to do the same question, and now we are going to use the right Riemann sum. Okay, so again, delta x is same as the previous one, so we're not going to calculate again. We are going to use, that was 0.5. Again, the sub intervals are same as the previous one, so 0 to 0.5, 0.5 to 1, 1 to 1.5, and then 1.5 to 2. So now we are going to use the right Riemann sum, means these right endpoints are going to determine the height of the rectangle, or here in the figure. So this right endpoint, so this is 0.5, this is 1, this is 1.5. So for the first rectangle, 0.5 is going to determine the height of the rectangle, so which is this rectangle right here. The second rectangle, this is going to determine the height, which is this rectangle right here. Third one, this is going to determine the height, which is this rectangle. The fourth one, this is going to determine the height, which is this rectangle. So now the area that we are looking at is this area right here, area of this rectangle right here, area of this rectangle right here, and then area of this fourth rectangle right here. Okay, so now let's go ahead and find the height. So now f, so heights are, so h-e-i-g-s-t-s heights. So f of 0.5 is, so 0.5, so for the first rectangle that's the height, so 0.5 is squared is 0.25, and then f of 1, which is 1, then f of 1.5, which is 2.25, and then f of 2, which is 4. Now the area, or the right Riemann sum, which is represented as R sub 4, is given by delta x, or f of, let's write it this way, f of x1 times delta x, because x1 is the height of the first, f of x1 is the height of the first rectangle, so f of x2 times delta x, f of x3 times delta x, plus f of x4 times delta x. And then, so f of x1 is 0.25 times 0.5 plus 1 times 0.5 plus 2.25 times 0.5 plus 4 times 0.5. And when we put this into the calculator, we get 3.75. Now let's go ahead and use the midpoint Riemann sum. Now in this case, we are going to use the midpoint to find the heights. Okay. Now we have the same delta x, which is 0.5, and we have the same sub-interval, so 0 to 0.5, 0.5 to 0.5 to 1, 0.5 to 1, 1 to 1.5, and then 1.5 to 2. But now to determine the height, we're not going to use left or right endpoint, but we are going to use the midpoint of this point. So the midpoint of this, okay, midpoint here, midpoint here. So in order to find the midpoint, what you can do is you can add these two and divide by 2. Okay, so when you do that, so for the first one, the midpoint is, so 0 plus 0.5 divided by 2 is 0.25. Now you can just keep adding 0.5 to get the next midpoint. So 0.25 plus 0.5, 0.75, 1.25, and 1.75. So those are the midpoints. Now here, this is x0, which is 0, right? And then we have 0.5, 1, 1.5, and 2. So those are the endpoints, but now we are going to use the midpoint. So the midpoint between 0 and 0.5 is 0.25. So this is the height of the rectangle. For this one, we are going to use this midpoint here. That gives us the height of the second rectangle. Now we are going to use this midpoint, and that gives us the height of the third rectangle. And we are going to use this midpoint that determines the height of the fourth rectangle. So now the area that we are looking at, this area right here, area of this rectangle, and then area of this rectangle, and then area is this area of that rectangle right here. So this looks a little bit better than the left or right sum. Okay, so now in order to find the sum, first we need to find the height, and then we're going to find the sum. So the heights of the rectangle are f of 0.25. So 0.25 squared gives us 0.0625. F of 0.75, that gives us 0.5625. F of 1.25, that gives us 1.5625, and then f of 1.75, that gives us 3.0625. You can just use your calculator to find that. Okay, now the midpoint Riemann sum with 4 rectangles, so m sub 4 is given by the height of the first rectangle 0.0625 times the width is same, which is 0.5, plus the height of the second rectangle 0.5625 times the width is 0.5, plus the height is 1.5625 times 0.5, And then the fourth rectangle height is 3.0625 times 0.5. And when we put everything into the calculator, we get 2.625. Now, the fourth question is asking us to compare the area that we obtained from using the left Riemann sum, right Riemann sum, and the midpoint Riemann sum. So if we go back to part A, where we obtained L sub 4 was 1.75, and then R sub 4 was 3.75, and then M sub 4 is 2.625. I don't say this is accurate, but this is better than these two areas. So this one, we can say, if we go back here to part A, okay, so this one 1.75. See, we are losing so much area here. This is what we are losing here, okay? So that means we can say these, the first one, this one, underestimates the area. And then if we look at the right sum, I think it overestimates because we have so much area gain here. So if you look here, this is the area that we are gaining. So we're not losing any area. So this overestimates. And this one is not accurate, but more close. I would say more close to the true area. Okay, it's not accurate, but if you look over here, see, we are gaining some area, but we are losing as well. So that kinds of balance, a little bit not exact, but it's much better than left and right. So it's kind of like close to what the exact area is, and we will later check what's the exact area under that curve. Okay. Now let's look at another example. So we are going to look at sine function, and we are going to do the same thing. We are going to find left, right, and midpoint Riemann sum. Okay. So here we are going to take six sub rectangles, I mean sub intervals, and we're going to go from 0 to, so this should be pi over 2, my bad, because we are looking at sine function. So it's not 2, it's pi over 2, okay? So now let's say the highest point is the pi over 2, so it's somewhere here. So I'm just going to say here's the highest point, that's pi over 2. So that is where we are going to go. And this is 0. So we are going to divide into 6 intervals, sub-intervals. So let's say these are the 6 sub-intervals. So we have x0, which is 0. And then let's go ahead and find delta x, which is pi over 2 minus 0 divided by 6, and that gives us pi over 12. So now here, let's go ahead and find the sub-interval. So I think in the graph it's really small to write that, so I'm going to write here. So the sub-intervals that we have is, the first one is 0 to pi over 12, because that is the width. So 0 plus pi over 12 is pi over 12. So the first sub-interval. The second sub-interval is pi over 12, comma, so add pi over 12 plus pi over 12, which is pi over 6. So the second point is pi over 6. Then the third one is pi over 6 to, when we add pi over 12 to this one, we get pi over 4. And the next one is pi over 4. Then add pi over 12 to this one, we get pi over 3. And then the third, and then the fifth one is pi over 3. Add pi over 12 to that one, so we get 5 pi over 12. And the last one is 5 pi over 12. When we add pi over 12, then we get pi over 2. So those are the intervals. Now first we are going to use the left Riemann sum. So the heights are, so we are going to evaluate the height at 0, pi over 12, pi over 6, pi over 4, pi over 3, and 5 pi over. We are going to use the left hand point to find the height. So the heights are sine of 0, sine of pi over 12, sine of pi over 6, sine of pi over 4, sine of pi over 3, and then sine of pi over 12. So those are the heights, okay? Now the left Riemann sum is given by So delta x times each height. So I'm just going to factor out delta x and I'm going to write this way. Okay, so this one times f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5. And then we don't go to the x6 because we are taking the left endpoint. We start at 0. So now delta x is pi over 12. Then this is sine of 0 plus sine of pi over 12 plus sine of pi over 6 plus sine of pi over 4 plus sine of pi over 3 plus sine of 5 pi over 12. So we don't put anything into the calculator right here, okay? So we're going to put everything together into the calculator at the end. And then when we put all of this into the calculator, we get 0.863, okay? So this is the approximated area. So in the next one, we're going to use the right endpoint. So okay, let's go ahead and construct this rectangle. We forgot to do that. So this one, the first rectangle is just 0. This is the second rectangle. This is the third rectangle. This is the fourth rectangle. This is the fifth rectangle. And then this is the sixth rectangle. So these are the areas that we are adding up with that left Riemann sum. Now let's go into the right Riemann sum. Again, the sub-intervals are exactly same, so I'm just going to write the height, okay? So I'm not going to write all of that. You can just look at the previous part A of this one. So the height now, the one that we are going to take this right endpoint. So for the height in the next slide, okay, for the height we are going to take this point. So this is the height. I mean, this will give the height. So these are the endpoints that we are going to take for the height, okay? So here, heights are sine of pi over 12, sine of pi over 6, sine of pi over 4, sine of pi over 3, sine of 5 pi over 12, and then sine of pi over 2. So here in the illustration, so we can do, so this is the pi over 2. So we'll divide into 6 sub-intervals. So right endpoint gives us the height now. This one is going to give us the height. Sorry, this one. So this is the height, that area that we are finding now. The right endpoint looks like it's going to overestimate because we are gaining a lot of areas. The left endpoints, the left Riemann sum underestimates because we were losing a lot of area, and that does not happen always. It depends on how the graph is. Okay. Now the right Riemann sum with 6 division is going to be, so the width delta x, which is pi over 12 times this height, so sine pi over 12 plus sine pi over 6 plus sine pi over 4. I'm going to write in the second row, okay, so plus sine pi over 3 plus sine 5 pi over 12 plus sine pi over 2. And then when we put everything into the calculator, we get 1.125. So there's the approximation of the area. Now let's use the midpoint. Now the midpoints are delta x is again pi over 12. So our intervals were, so if you remember, 0 to pi over 12, and then pi over 12 to pi over 6, then pi over 6 to pi over 4, and then pi over 4 to pi over 3, then pi over 3 to 5 pi over 12, and then 5 pi over 12 to pi over 2. So those are the subintervals. Now for the midpoint Riemann sum, we need to find the midpoint of these subintervals. Okay, so we need to find the midpoint of this. And again, what you are going to do is you are going to add those two and divide by 2. So you can keep, so don't put pi in the calculator. So for the first one, you can do 0 plus 1 over 12 divided by 12. That gives us 1 over 24, but we have that pi, so you can write pi over 24. And then after that, you can just keep adding pi over 12 to get the next midpoint and so on. So I'm going to list the midpoints here. So the midpoints are, the first one is pi over 24, we found that. Now if we add pi over 12 to that one, so we get pi over 8, then we get 5 pi over 24. So just keep adding pi over 12. Okay, so 7 pi over 24, and then 3 pi over 8, and then 11 pi over 24. So here in the graph, so these are our divisions. Okay, so these are the 6 subintervals. So what we are going to do is we are going to use the midpoint to determine the height. So that gives the area. So midpoint of that one gives the area. So midpoint here, that gives the area of the rectangle. So midpoint here, it's really hard to draw here, but yep, that's how it might look like. The midpoint here is the height of the rectangle, and then this is the height of the rectangle. So this one midpoint looks a little bit better. It doesn't seem like we are losing a lot or gaining a lot, kind of like balances with each other. Okay, so now the midpoint Riemann sum with 6 divisions is given by, so delta x, which is pi over 12 times the height at this point. So sine, so the function sine gives us the height. So sine pi over 24 plus sine pi over 8 plus all of these. I'm just going to write it that way. I think you can write it down. And then put everything into the calculator and we get 1.00286. So let me tell you, so the area under the sine curve from 0 to pi over 2, so this is not 2, okay, so this is pi over 2. So that is given by, that is equal to actually 1 is the exact area. Now if we compare here, the first one gave us 0.863, that means that is underestimated. This is over 1.12, so it's overestimated. This is still overestimated, but it's very close to 1. So midpoint is giving us a little bit more accurate area. Okay, it's not accurate, but it's very close. So now we looked at examples where we divided the rectangle into some small number of uh, we divided the region into some small number of rectangles, like just 4 or 6. But now, as I said, to get better area, we need to divide that into more or a large number of rectangles, maybe 50, 60, 100, maybe 1000, and then we want to go to infinity. So now, if we are given like n equals 50 or 40 or 100, it's really hard to do all of that by hand, drawing those rectangles and finding the height of each rectangle, 50 different rectangles. It's a lot of work, tedious, and that gets so much messy. So now what we do is we are going to use the sigma notation in order to find the sum, okay? So again, it's the same definition here. So again, this is the Riemann sum we already looked at. This gives us the Riemann sum. Now it becomes a left Riemann sum if x sub k star, so the point that determines the height, is a, so the starting point, plus k minus 1 times delta x. So that gives us the determining point, the left endpoint of each subinterval. Now the right endpoint of each subinterval is given by a plus k times delta x. And the midpoint of each subinterval is given by a plus k minus 1 half delta x. So when we use this in terms of using n equals 4 or 5, so if we make it more general, then we can use more number of rectangles, and we can use a calculator actually to find this sum. Okay, so let's look at an example here. So now we are going to find left, right, and midpoint Riemann sum for this function on that interval with n equals 40. So the first thing that we are going to do is always that's the case. Okay, so we are going to determine delta x. So the width of the rectangle. So delta x equals b minus a over n. So which is 5 over 40 or 1/8. Now again, so we are not going to construct the rectangle like we are not going to find the height by hand for each subinterval or each rectangle. What we are going to do is we are going to generalize this. Okay, so for left Riemann sum, we know that we are going to use this one. So the point that determines the height is given by a plus k minus 1 times delta x. So x sub k star is given by a, which is 0, plus k minus 1 times delta x, which is 1/8. So if we simplify this, we get k over 8 minus 1 over 8. Now what we do is, if you look back here at the function, the sum is given by delta x times f of x k star. So what we are going to do is we are going to find f of x k star, which means f of x is x cubed minus 2 and x k star is right here, so that becomes x cubed means k over 8 minus 1 over 8 cubed minus 2. Now the left Riemann sum with 40 subintervals is given by the sum k equals 1 to n, means n is 40, then f of x sub k, so this is the formula, okay, right here. So f of x sub k star, which is this one here, k over 8 minus 1 over 8 cubed minus 2, then we multiply this one by delta x. So this one times delta x, which is 1/8. Now again, this is really hard to evaluate by hand, so we are going to put the whole thing into the calculator, and if you do that you are going to get approximately. So I have linked a video in the description, so you can use that video to determine or to find this sum in a calculator. Okay, so we are going to use a calculator here. So if you put this into the calculator, you are going to get 138.535. So that is the approximated area. Now let's go ahead and do the right Riemann sum. Now for right Riemann sum, x sub k, or the point that determines the height of the rectangle, is given by a plus k times delta x. So a is 0, k is k, delta x is 1/8, so k times 1/8 is just k over 8. Now f of x sub k star for this one is, we'll take this one and we'll put it into our function. So it is k over 8 cubed minus 2. Now the right Riemann sum is given by k equals 1 to 40 f of x sub k star, so which is k over 8 cubed minus 2. Then we multiply this one by delta x, which is 1/8. Again, if we put this into the calculator, we are going to get 154.16. Now, the third one is the midpoint Riemann sum. So for midpoint Riemann sum, again, we are going to do some midpoint Riemann sum. X sub k star is given by, so a plus k minus 1/2 delta x. So a is 0, so k minus 1/2 delta x is 1/8. So when we multiply this, we get k over 8 minus 1 over 16. Now f of x sub k star, or the height, is given by, you plug that into the, so you take this one and put it right here, so you get k over 8 minus 1 over 16 cubed minus 2. Now the midpoint Riemann sum is is summation k equals 1 to 40. Now f of x sub k star, which is k over 8 minus 1 over 16 cubed minus 2. We multiply this one by delta x, which is 1/8. Again, if we put this into the calculator, you're going to get 146.2. So this is the area under the curve. So they are pretty much close with each other. So 138, 154, 146. But I'm pretty much sure that this is going to be more accurate or more close to the exact area. Now the final thing that we are looking at, see, as we increase the number of rectangles, we are going to get better and better area. So maybe this one gave us a little bit better area, but that's again not exact. So in order to find the exact area, what we are going to do is we will find the Riemann sum with n rectangles. So we're not going to specify what n is. We'll just take n. And then we'll take the limit n approaches infinity. That means that's going to give us the exact area under the curve. So let's look at one problem on this one, and then we'll stop the video for today, okay, after doing this problem. So here the function is again x cubed minus 1, and we are going to evaluate the area under the curve on the interval 0 to 2. We are going to do exact one. We are going to use the right Riemann sum here, okay? And then we'll take the limit. So again, the first thing that we are going to do here is find the width of the rectangle delta x, which is b minus a over n. And again, we don't know n, so we are going to take n to the infinity, but we cannot put infinity now. We'll just take the limit later, so we'll just leave this as 2 over n. Now we're going to use the right Riemann sum, so x sub k star equals, so a plus means 0 plus k times delta x, so which is just 2k over n. And then we need to find the value of the function here, so we'll plug it in here, but let me go and write the right Riemann sum with n subdivision is given by k equals 1 to n, then f of x k star, that means we'll take this one and put it into our function, so 2k over n cube minus 1, that's the function, times the height, okay, which is again 2 over n. Now this equals summation k equals 1 to n. Then when we do this, we get, sorry, I think my function, I wrote the wrong function here. This should be squared. That's what I was taking here. Okay, so let's change the question. This is a squared. So now we have 4k squared over n squared minus 1 times 2 over n. Now when we distribute that 2 over n, so we get 8k squared over n cubed minus 2 over n. And what I'm going to do is I'm going to separate this summation. I'm going to write k from 1 to n, 8k squared over n cubed minus, again, sum 2 over n. So k goes from 1 to n. So now from here, see, we really have to be careful here. Our variable is k, not n. N is a fixed number, constant. So we can factor out n. So what we do here is, and we can factor out that 8. So we can factor out 8 over n cubed. And then we have k equals 1 to n k squared minus, we can do the same thing here. We can factor out 2 over n. And we have k equals 1 to n, and then we just leave 1 here. Now for the first one, this is the sum of the squared of natural numbers. So if you watch the previous video where we did this summation, the sigma notation, so you know that sum of these, sum of the squares of natural number is given by, so I'm going to write the formula here. So this equals, so we have 8 over n cubed times, so this sum is given by n times n plus 1 times 2n plus 1 divided by 6, and then minus, we have 2 over n. So this is summation of one from 1 to n. That means we are adding 1 plus 1 plus 1 up to n times, which is just 1 times n, and that's just n. Okay, so this sum right here, this is n. Now we have 8 over, so we can bring that 6 out, and then we can cancel the common factor of 8 and 6, which is 2, so we'll get 4/3 and then n cubed. So we can multiply here, so n times 2n gives us 2n cubed plus n times n squared times 1 gives us n squared plus 1 n times 1 is n times 2n gives us 2n squared plus n times 1 is n times another one is n, and then we have minus 2. So 4 over 3n cubed, and then if we combine this, we get 2n cubed plus 3n squared plus n minus 2. So now if we distribute this, we get, so when we multiply the first one, we get 8 over 3, and n cube cancel out. So we don't have any n. So when we multiply with the second one, 3 and 3 cancels out, so we have 4 over n. And then when we multiply with the third one, we get 4 over 3n squared minus 2. So this represents the Riemann sum in terms of n. Now the true area is given by the limit as n approaches infinity of r sub n, or the Riemann sum. So now let's go ahead and evaluate the limit. So limit n approaches infinity, 8/3 plus 4 over n plus 4 over 3n squared minus 2. So this limit, so when we find the limit, what happens? So this goes to 0, this goes to 0. So all we have here is 8/3 minus 2, which is 2/3. And that is the exact area under that curve from 0 to 2. Again, this function, I changed the question, so this is, actually I have a typo here, this is x squared minus 1. That's what I was planning to do here. Okay, so we'll just stop here for this video. In the next video, we'll talk about the definite integral. So we'll start from this point, okay, what we did here in example 4.